In this section, we're going to be looking at convergence properties of Fourier series. Essentially, this is dealing with some of the more mathematically subtle issues that revolve around infinite sums. Because a Fourier series is a summation that can involve an infinite number of non-zero terms, there's always the possibility that things can go wrong when these terms are being summed. Either the sum doesn't converge at all, for example, it blows up to infinity, or the sum doesn't converge to the particular function to which we want it to converge. Before looking at convergence properties of Fourier series, I first need to make some comments regarding the equality of functions. Essentially, the matter of concern here is what does it mean for two functions to be equal? And as it turns out, this is not so straightforward. There's more than one reasonable way to define the equality of functions. Arguably, the most straightforward way to define the equality of functions is in a pointwise sense. So two functions x and y are said to be equal in the pointwise sense if this particular relationship here is satisfied. In other words, the function x is equal to the function y at every point, hence the term pointwise equality of functions. But this is not the only sensible way in which we can define the equality of functions. Another very important definition, which is used quite pervasively in engineering, is equality of functions in the mean squared error sense. So if you have two functions x and y that are equal in the mean squared error sense, what this means is that this particular relationship is satisfied. In other words, if we treat the difference between the two functions x and y as an error and we take the magnitude squared of this and integrate, the result we get is 0. This is what it means for two functions to be equal in the mean squared error sense. And essentially what this is saying is that the energy and the difference between the two functions, in other words x minus y, is 0. And it turns out this is a very useful definition of equality in many contexts. Another comment I can make with respect to these different types of equality is that pointwise equality is a much stronger condition than mean squared error equality. In other words, pointwise equality implies mean squared error equality, but the converse is not necessarily true. Now maybe to illustrate these concepts by way of example, let's consider the three functions that are shown on this slide, the functions x1, x2, and x3. So x1 is simply defined to be a function which is equal to 1 for all t. The function x2 is defined to be a function which is equal to 1 for all t. And then we have this function x3, which is defined to be 1 almost everywhere. It's equal to 1 everywhere except at the origin, where the function is equal to 2. Now let's consider comparing the functions x1 and x2. So as it turns out, x1 and x2 are equal in both the pointwise sense and the mean squared error sense. So let's look at this more carefully to see why this is so. If we look at the formula for x1 of t and the formula for x2 of t, you can see that these expressions will be equal for all values of t. Therefore, by definition, x1 and x2 are pointwise equal. In other words, they're equal in the pointwise sense. But x1 and x2 are also equal in the mean squared error sense. To see this, we simply need to look at the relationship that needs to be satisfied for two functions to be equal in the mean squared error sense. In other words, this condition that I've highlighted. So in this particular case, we're going to substitute in for x and y the functions x1 and x2. And when we do this, because x1 and x2 are equal at every point, what we end up with for the integrand here, in other words, the function that we're integrating, is just 0. And integrating 0 will give us 0, so this condition will be satisfied. Therefore, x1 and x2 are equal in the mean squared error sense. Now let's consider comparing the functions x1 and x3. So as it turns out, x1 and x3 are equal in the mean squared error sense, but not in the pointwise sense. So let's look at this in more detail and see why this is so. First, let's consider the pointwise sense of equality. So if we compare the functions x1 and x3, you'll see that these functions are equal everywhere except at the origin, where x3 is equal to 2 and x1 is equal to 1. So because these functions differ at least one point, these functions are not equal in the pointwise sense. Now let's consider the case of equality in the mean squared error sense. So looking at the definition of equality in the mean squared error sense, what we're interested in is an integral of this form, where x and y in this formula correspond to the functions that we're comparing for equality. So in this case, we're going to substitute for x and y the functions x1 and x3. And when we do this, what we're going to end up with is a function that's 0 everywhere except at the origin, because x1 and x3, these two functions, are equal everywhere except at the origin. So when we take their difference, we'll get a function that's 0 everywhere except at the origin. And at the origin, because one of these functions is equal to 2 and the other function is equal to 1, we'll either get minus 1 or plus 1 when we take the difference between them. But it doesn't really matter whether it's minus 1 or plus 1 because we're immediately going to take the absolute value. So we're always going to get 1 after the absolute value operation, and then we square, which would give 1 squared, which is 1. So what we end up in the integrand here is a function that's 0 everywhere except at the origin, where the function's equal to 1. And if we integrate such a function, what we'll end up with for the result is 0, because effectively what we have is the area of a rectangle where the width of the rectangle is 0 and the height of the rectangle is 1, and 0 times 1 is equal to 0. Therefore, this particular condition for equality in the mean squared error sense is satisfied. Therefore, x1 and x3 are equal in the mean squared error sense. Now that we've been introduced to the notions of pointwise equality and mean squared error equality of functions, we're ready to begin examining the convergence properties of Fourier series in detail. And as we'll see shortly, both of these notions of equality will play a key role in this discussion. At this point, I'd like to introduce the issue of convergence for Fourier series. So if you recall, if we have a periodic function x that we wish to represent with a Fourier series, essentially we're using a summation of this form. In other words, the Fourier series looks like what's highlighted here. And the thing to note about this summation is that you're summing an infinite number of things, right? Because we're summing over all integer k, and there are infinitely many integers. Therefore, we have an infinite number of terms that are being summed. And because we have the possibility that all of these ck values are non-zero, we have the potential to be summing an infinite number of non-zero terms. And when we try to calculate such a sum, bad things can happen. We can have the whole summation blows up to infinity or fails to converge for other reasons. So essentially what we're dealing with when we're talking about convergence for Fourier series is if we have some periodic function x, and we're saying that it has this Fourier series given by this formula here, is this actually a meaningful thing to say? In other words, is this function x really actually equal to this Fourier series in some sense? And this is what we're dealing with when we're dealing with convergence. So to help address the issue of convergence and look at it in more detail, I'm going to define this function x subscript capital N in the following way. It's given by this particular formula here. So all this is just a truncated version of the original Fourier series that's given on the line above. So we've just taken the summation from minus infinity to infinity and thrown away a whole bunch of terms, taking the summation from minus n to n. And more formally, what we're talking about when we're talking about the convergence of Fourier series is if we take the limit of this function x subscript n as n goes to infinity, in other words, we take this limit here, is the result that we get, the resulting function, is this function equal in some sense to x? Where the sense in which it's equal to x might be in terms of pointwise equality or in terms of mean squared error equality. But if this quantity here is not equal to x in some sense, essentially what that's saying is the Fourier series is not adding up to anything that even in any way represents x, because it's not equal in any way to x. So this is essentially what we're dealing with when we're talking about convergence, is this limit actually equal to x in some sense? If it's not, then Fourier series are not going to be very helpful to us, because they don't represent x in any sort of meaningful way to begin with. So now we're just continuing from the previous slide. So just to refresh your memory, we're using x subscript n to denote the Fourier series for the periodic function x truncated after the nth harmonic components. In other words, x subscript n is given by this particular truncated Fourier series here. Now suppose that this particular condition is satisfied. In other words, if we take the limit of x subscript n as n goes to infinity, suppose that gives us a function which is pointwise equal to x. Then we say that the Fourier series converges pointwise to x. If, on the other hand, we have a relationship of this form satisfied, so in this case we're taking the limit as n goes to infinity of this particular integral, and this particular integral corresponds to the energy in the difference between xn and x. If this is equal to 0, in other words, what we're saying is that the limit of xn as n goes to infinity is equal to x in the mean squared error sense, then we say the Fourier series converges to x in the mean squared error sense. And pointwise convergence is a stronger condition than mean squared error convergence. In other words, pointwise convergence implies mean squared error convergence, but the converse is not true. Lastly, I just want to introduce one additional term, which is uniform convergence. So if convergence is pointwise, and it's at the same rate everywhere, we say the convergence is uniform. So in other words, uniform convergence is just a special case of pointwise convergence, where the convergence is happening at the same rate everywhere. The first convergence result that I need to present for Fourier series relates to continuous functions. So suppose that we have a periodic function x that's continuous, and its Fourier series coefficients are absolutely summable. This is just a fancy way to say that if you take the magnitude of all the Fourier series coefficients and add them up, you get a finite value. If these conditions are satisfied, then the Fourier series representation of x converges uniformly. In other words, it converges pointwise and at the same rate everywhere. Now in practice, we often encounter functions with discontinuities, for example, something like a periodic square wave. So for this reason, the above result is somewhat limited in value. In other words, the conditions that need to be satisfied for this result to be useful, for example, the function needs to be continuous, are sometimes not satisfied. So this result is sometimes useful, but sometimes not, because the conditions are not always satisfied for functions that are of practical interest. The next convergence result that I need to present for Fourier series relates to functions with finite energy in a single period. So suppose that we have a periodic function x with finite amount of energy in a single period. In other words, this particular integral here is finite. Then the Fourier series converges in the mean squared error sense. Now in practical situations, usually this condition of finite energy is going to be satisfied. So for this reason, this particular result is often applicable. It's important to note, however, that mean squared error convergence doesn't necessarily imply pointwise convergence. So for this reason, knowing that the Fourier series converges in the mean squared error sense doesn't tell us the particular numerical values that it will converge to at particular points. So this theorem is not very useful in situations where we want specific numeric values for what the Fourier series converges to at particular points. So for this reason, this particular result on this slide relating to convergence of Fourier series is usually mostly helpful for just determining whether the Fourier series converges or not, but not the specific numeric values that it converges to. Before I can present the next convergence result for Fourier series, I first need to introduce what are known as the Dirichlet conditions for a periodic function. So the Dirichlet conditions are a set of three conditions that a periodic function may or may not satisfy. So let's look at these conditions in more detail. So for the periodic function x, the first Dirichlet condition is over a single period, the function x is absolutely integrable. In other words, this particular integral here converges to a finite value. And this integral is simply taking the magnitude of the function x and integrating it over a single period, which is denoted by capital T here. The second condition is that over a single period, the function x has a finite number of maxima and minima. In other words, x is of bounded variation. And what this means is simply the function doesn't oscillate infinitely fast. The third condition is over any finite interval, the function x has a finite number of discontinuities, each of which is finite. So there's two parts to this. First of all, the number of discontinuities is finite. And secondly, each discontinuity in the function, in other words, each jump in the function is by a finite amount. So on the bottom of this slide, I have some examples of functions that violate the Dirichlet conditions. An example of a function that violates the first condition is the one shown in this graph at the top left. So what I have in this graph is I've taken the function 1 over t and extracted out the portion of the graph from 0 to 1. And then I've periodically repeated this with period 1 to get this periodic function that's shown here. Now this particular function violates the first Dirichlet condition because if we try to integrate the absolute value of this function over a single period, for example, consider the period from 0 to 1, when we integrate 1 over t, we're going to get a logarithmic type function. And when we evaluate this logarithmic function at 0, it's going to blow up to infinity. So because of this, this function is not absolutely integrable. An example of a function which violates the second condition, the condition of bounded variation, is this function here, and shown in this top right graph. So what this corresponds to is I've taken the function sine of 2 pi over t, and I've cut out the portion of the graph from 0 to 1, which looks something like what's shown here, and then periodically repeated it with period 1 to generate this periodic function. Now this particular function violates the condition of bounded variation. The reason why is in this little portion of the graph going from 0 up until where the mouse is here, this little section here, there's an infinite number of oscillations of this function. As this function gets closer and closer to 0, moving from the rightward direction, or moving from the right in the leftward direction towards 0, this function oscillates more and more quickly, and this last little portion of the interval from where we are here to 0 includes an infinite number of oscillations. So this violates the condition of a finite number of maxima and minima. And then in the third graph, the one at the bottom of the slide, this is an example of a function which violates the third Dirichlet condition. And this particular function here, what it is, it's a sequence of steps, essentially like a staircase, where each step in the staircase is half the size of the previous step. So this first step has a width of 1/2 and a height of 1/2, and then the next step has a width of 1/4 and a height of 1/4, and so on, at 1/8, 1/16, and so on. This last little portion here that's not fully drawn in, it turns out that there's an infinite number of steps in this staircase to get to the point 1 from this last step that's actually shown. So because of this, this particular function violates the requirement that you cannot have an infinite number of discontinuities over any finite interval. Here we have a finite interval, this little section here, that has an infinite number of discontinuities. And probably the main observation that I'd like to make with respect to these functions is that you're probably not likely to encounter functions like this in practice. In other words, most functions that you're likely to encounter in a practical real-world situation are likely to satisfy the Dirichlet conditions. The last convergence result that I need to present for Fourier series relates to functions that satisfy the Dirichlet conditions. So if a periodic function x satisfies the Dirichlet conditions, then there are a number of things that we can say about how the Fourier series for the function x converges. In particular, the Fourier series for the function x will converge pointwise everywhere to x, except at the points of discontinuity of x. And furthermore, at each point of discontinuity of x, which we denote by TA here, the Fourier series will converge to the average of the left and right limit of the function x at that point of discontinuity. Now in practice, most functions tend to satisfy the Dirichlet conditions, so for this reason this particular convergence result is quite useful because it specifies not only whether the Fourier series converges or not, but it also specifies the particular numeric value that the Fourier series converges to at each point. So this particular result is quite useful, for example, in problems where we need to compute a specific numeric value for what the Fourier series converges to at a point. At this point, I'd like to consider an example to illustrate how we can use the convergence result on this slide for the Dirichlet case. And in particular, I'd like to consider example 5.6. In this example, we're given a periodic function x with the fundamental period capital T equal to 2, that's shown in figure 5.4, so this function here. And we're asked to let x hat denote the Fourier series representation of x. In other words, x hat is equal to this expression here, where omega naught is equal to pi. Because if the fundamental period t is equal to 2, then the fundamental frequency must be equal to pi. And in this example, what we're asked to do is determine what the Fourier series will converge to at the point 0 and at the point 1. So to do this, what we're going to use is the result about convergence that relates to functions that satisfy the Dirichlet conditions. Because the first observation we can make here is this function x that we're given satisfies the Dirichlet conditions. Again, so there's three conditions. The first condition is that the function must be absolutely integrable over a single period. So if we integrate the absolute value of this function from 0 to 2, for example, over a single period, we get a finite value, so the function is absolutely integrable. The second condition is the function is of bounded variation. In other words, over a single period, the function has a finite number of maximum and minima. It can't oscillate infinitely fast, and clearly this is satisfied by this function. And then the last condition is that over any finite interval, the function must have a finite number of discontinuities, and each discontinuity must be a jump by only a finite amount. And clearly this condition also is satisfied by this function. So because the Dirichlet conditions are satisfied, we can use the result which relates to Dirichlet conditions in order to solve this problem. So if we want to evaluate the function at the point t equal to 0, so this point here, we observe that at t equal to 0, this function has a discontinuity. So the convergence result that relates to the Dirichlet condition says at points of discontinuity of the original function, the Fourier series will converge to the average of the left and right limit at that point of discontinuity. So if we look at the graph here, as we're approaching this point of discontinuity t equal to 0 from the left, the value that we see is 0. And as we're approaching the discontinuity from the right, the value that we see is 1. So the Dirichlet, the result that relates to the Dirichlet condition says that the Fourier series will converge to the average of the left and right limit at the point of discontinuity. So it will converge to the average of 0 and 1, which is simply 1/2. Then we need to compute what the Fourier series converges to at the point t equal to 1. So again, we look at the point t equal to 1 on our graph and observe there's another discontinuity in the function x here. So again, the Fourier series will converge to the average of the left and right limit at this point of discontinuity. So as we're approaching the discontinuity at t equal to 1 from the left, the value that we see is 1. And as we're approaching from the right, the value that we see is 0. So the average of these two values, in other words, the average of the left and right limits as we're approaching this discontinuity, is going to be the thing that the Fourier series converges to. So the average of 1 and 0 is simply 1/2. In practice, we often encounter periodic functions with discontinuities. And when a function x has discontinuities, the Fourier series representation of x does not converge uniformly. In other words, it doesn't converge at the same rate everywhere. And in particular, the Fourier series will converge much more slowly at points in the vicinity of a discontinuity. Now, in practice, when we employ Fourier series in computer algorithms, we must always truncate the Fourier series to a finite number of terms, otherwise the computation would never finish. So if we let x subscript n denote the Fourier series truncated after the nth harmonic components, in the vicinity of a discontinuity, x subscript n exhibits ripples. Furthermore, as n increases, in other words, as fewer terms in the Fourier series are discarded, the ripples are compressed towards the discontinuity, but the peak amplitude of the ripples remains approximately constant for any finite n. And this particular behavior is known as Gibbs Phenomenon. And this is one of the weaknesses of Fourier series, namely in the vicinity of discontinuities, they converge very slowly and exhibit a high degree of oscillatory behavior. On this slide I have a simple example to illustrate Gibbs phenomenon, but rather than going through the example on this slide, I'm going to go through the example on an annotated version of this slide. On this slide I have a simple example to illustrate Gibbs phenomenon. In this example we consider approximating a periodic square wave using a Fourier series that's truncated after the nth harmonic components so that only the terms with the indices minus n to plus n in the Fourier series are kept. The four graphs shown on the slide correspond to different choices of n. In each graph, the original square wave is drawn using a dashed line, and the Fourier series truncated after the nth harmonic component is drawn using a solid line. So in the top left figure, this corresponds to n equal to 3, the top right figure corresponds to n equal to 7, the bottom left figure corresponds to n equal to 11, and the bottom right figure corresponds to n equal to 101. And as you can see, as we move from the figure in the top left to the figure in the top right, to the figure in the bottom left, to the figure in the bottom right, we're getting a progressively better approximation of our original periodic square wave. In other words, our truncated Fourier series is giving a better approximation as we add more and more terms into the truncated Fourier series. Looking at these figures, however, we can observe another effect. In particular, in the vicinity of points where the original function has discontinuities, the truncated Fourier series exhibits considerable oscillatory behavior. For example, consider the discontinuity that appears at 0.5, in other words, this point here. You can see that just to the left of this discontinuity, instead of the function having the value 1, it overshoots the value of 1 and goes a little bit larger than it should. And we see this similar sort of behavior in the other graphs as well. At the discontinuity at 0.5, we get this overshoot. Just before the discontinuity, the function goes larger than it's supposed to. It goes above the value 1 and overshoots the desired value. And we see a similar overshoot in the graph in the bottom left, and a similar overshoot in the graph in the bottom right. So the interesting thing to note here is as we increase n, in other words, we increase the number of terms in the Fourier series, it doesn't really seem to affect the size of the overshoot. The amount of overshoot in all these graphs is about the same. And it turns out that even if we increase the value of n to an astronomically large finite value, the amount of overshoot is about the same. The only way to get rid of this overshoot is to actually include all infinity of terms in the Fourier series. The only effect that increasing n has with respect to these oscillations that are caused by the discontinuities is as we increase n, the oscillations due to the discontinuities get compressed closer and closer to the discontinuity. So here you can see the bulk of the oscillations, the very large oscillations, are happening very, very close to the discontinuity, whereas here they spread out a little bit further from the discontinuity. So as we're increasing the number of terms going from the bottom or top left to the top right, to the bottom left, to the bottom right, the oscillations are being compressed closer and closer to the points of discontinuity, but again, their amplitude doesn't really change in any appreciable way. And this particular effect is known as Gibbs phenomenon. And finally, I'd like to make one last comment about this example. Earlier we talked about uniform convergence. This particular example is a very good example of convergence that is not uniform, in other words, non-uniform convergence. And what I mean by this is as we're going from the figure in the top left to the figure in the top right, to the figure in the bottom left to the figure in the bottom right, in other words, as we're progressively adding more and more terms into the Fourier series, it does appear that the Fourier series is converging pointwise to our periodic square wave, and in fact this is the case. But the important observation to make is that the convergence is not happening at the same rate everywhere. For example, if we look at the figure in the bottom right, this particular approximation using a Fourier series is starting to become reasonably close to our periodic square wave, but you'll notice that the goodness of the approximation is not the same everywhere. In places that are further away from the discontinuity, like in this region here, the approximation that's given by the Fourier series is pretty close to our square wave. On the other hand, points that are close to the discontinuity, like in this region here, are very, very poor approximations to our square wave. In other words, the Fourier series is not converging to a square wave at the same rate everywhere. So this is an example of non-uniform convergence.